Hello everyone, welcome to Digital Electronics lecture series. This is lecture number 12 and we'll be doing Boolean theorems. So let us start with the Boolean theorems because these theorems will be used for designing the digital circuits. So first we take on the laws of ORing. We study the laws of ORing. The first one, A or 0 is equivalent to A. Then A or 1 is equal to 1. Then A or A is equivalent to A. And the fourth one, A or A bar is always equal to 1. So these are the laws of ORing. This ORing or all the other laws which we will be studying, they are used in designing the digital circuit. They are used for reducing the expressions. So if we reduce the expressions, then our circuit becomes compact. Less number of gates would be required. We can verify this. Suppose we have a OR gate. This is the OR gate. We can verify all the laws what we have written here. So this ORing means we have this OR gate. So the first one is this one, A or 0. Now A is a variable. A can have either, it can be 0 or 1. Other input is 0. So we know if A, suppose if we make A equal to 0, so 0 0 is 0. And if we make A equal to 1, then 1 0 or is 1. So whatever is A, we get at the output. So therefore A or 0 is always equal to A. Then next one also we can verify. Here we have A, here we have 1. So we know even if a single input is 1, output becomes 1. So irrespective of what A is, this is always 1. So this is also verified. Then the third one, A, both inputs are A. So if A is 0, both are 0. So 0 0 is 0. And if we have 1, so both are 1, 1 1 is 1. So this is A or A is A. It is not 2A, it is A. Then A or A bar. Suppose this is A bar, this is A and this is A bar. So if A is 0, this becomes 1. So one of the input is 1, so output becomes 1. And if this is 1, and so this is 0, so at least one input is 1, so this is always 1. So A or A bar is always 1. So this is the laws of ORing. Now next we see is laws of ANDing. So next is laws of ANDing. The first one, A and 0 is always 0. Second, A and 1 is always 1. Third one, A or A is always A. And the fourth one, A and A bar is always 0. Let us verify them. We can have an AND gate here. So first is A and 0. So any input is 0, output becomes 0. So this one is verified. Next is A and 1. So 1. Now A is a variable. So A is a variable means A can have either 0 or 1. So if A is 0, output is 0. And if A is 1, output is 1. So A and 1 is always A. Then A and A. If A is 0, both inputs are 0, output is 0. If A is 1, both inputs are 1, output becomes 1. So A dot A is A or A and A is A. Then A and A bar. Now A and A bar. So if we take A equal to 0, this becomes 1. So one of the input is 0, so this becomes 0. Now if A is 1, so this becomes 0 then. A is 1, A bar becomes 0, again this is 0. So A and A bar is always 0. Now next we see the laws of complementation. Laws of complementation. This is with respect to the NOT gate. So laws of complementation. The first one says if A is 0, then A bar is 1. and if a is 1, a bar becomes 0. Then we can have second one is a double bar is a itself. So if we take the complementation of a twice, if we complement a twice, it becomes a itself. Then the third says that complement of 0 is 1, and fourth says complement of 1 is 0. Here there is no need for verifying using the NOT gate. It's straightforward. If you have to, you can even verify using a NOT gate also. Okay, so if this is 0, this is 1, this is 1, this becomes 0, and so on. And if we revert it, if we connect one more NOT gate, so this one will become 0. Okay, and this one will get, so this is double negation is the variable itself. So this is the laws of complementation. Next we have a commutative law. So commutative law for AND is this one: A and B is equal to B and A or B equal to B or A. This is the commutative law. Then we have associative law, that we have A and B and C. This is in the bracket. It is equal to A dot B and C. Same way, A or B or C is equivalent to A or B or C. Now next is DeMorgan's laws. So there are two laws, first law and second law. The first law says that the complement of the sum is equal to the product of the individual complements. So A or B the whole bar is equal to A bar and B bar. So we can replace this one by this, both are equivalent. So this is the first law. If you draw the circuit diagram, also if you draw this diagram of with respect to gates, so first is OR gate. This is the OR gate. So this is A, B. So A and B, A or B, and then here we have a NOT gate to complement the entire A or B. So here we have A or B the whole bar. Then on the right hand side we have a AND gate, but first we have the complemented input. So input should be complemented before applying to the AND gate. So this is A, this becomes A bar, this is B, this becomes B bar. Now we have to take the AND. So and here we have the AND. So this both are equivalent. This is what DeMorgan's law says. Let us verify them. So what we have to prove is, in this case, this we have to prove, and this is equal to this A or B the whole bar. So what we have to prove this to. So we have two inputs, so 0 0 0 1 1 0 and 1 1. So what we require is, we require A bar and we require B bar, and we also require A or B, so that finally we can complement here. So A bar is a complement of A. So this is 0, this becomes 1. This is 0, this becomes 1. This is 1, this becomes 0. This is 1, this becomes 0. So A bar. Same way B bar is complement of B. This 1, 0, 1, 0. Now A or B, we have to OR A and B. A, B, we have to OR. So the rule for is, even if a single input is 1, output becomes 1. So this is 0 first, because both are 0 0 and rest all are 1 1. Now we have to do A bar and B bar. So and A bar B bar. So the rule for AND says that when both the inputs are high, output is high. So this is the one input combination where both are 1. So this becomes 1. So this becomes 1, and rest all becomes, because there is a single 0 or more than there are either single or two zeros. So this becomes 0, this becomes 0, this becomes 0. Now to take this A or B the whole bar. So this is A or B. This is A or B. We have to complement this. So wherever 0 comes, 1 will come, wherever 1 comes, 0 comes. So here we have this 1 0 0 0. So this is verified. This is equivalent, because both are same for the input combination 0 0 both are 1, 0 1 both are 0, 1 0 both are 0, 1 1 both are 0. So this we have verified the DeMorgan's law. Now next is DeMorgan's second law. Second law says the complement of the product is equal to the sum of the individual complements. So we have this A and B, the whole bar is equal to A bar or B bar. So we can replace this by this. So how to draw the diagram for this? We have the diagram for, first of all, A and B. So we have AND gate. Sorry, this is not AND gate. AND gate. We need to draw AND gate. So this is the AND gate. So this is input A, input B, A and B, and they are complemented. So up to here we have A and B, and this becomes A and B the whole bar. So this is equivalent to, first we have to complement the two inputs A and B. This is A, this is B. So then we have to take the OR. So this is the OR. So this becomes A bar or B bar. So these two are equivalent. So this is actually A bar and this is B bar. Next we verify using the truth table. So for verifying using truth table we need A bar, B bar, then here we need A or B, A and B, then A and B the whole bar, and then finally A bar or B bar. So we have to verify this individually. Then same way procedure, complement of A, complement of B, A and B. So A and B is high when both the inputs are high. So this is 0, this is 0, this is 0, last is 1 because these two are 1. Then we have to complement this. Complement of this A and B, we have to take it and write it here. So complement of 0, I will just change the take a yellow one. So this is 1. This, let me take blue one. So this is 1, this is 1, this is 1, this is 0. Now we have to take the OR of A bar B bar. So this is A bar B bar is here, this is A bar B bar. So OR rule is when both are 0, it is output is 0. So this is 1, this is 1, this is 1, and finally this one, both are 0. So this becomes 0. So now it is verified. This is the verified, you can see. So this is how we verify the second law. Now let us see some definitions. The first is literal. So any variable in a Boolean expression can be called as a literal. It can be uncomplemented or complemented form. Suppose we have Boolean expression y equal to A bar plus B D plus C bar. This is the expression. So here A bar is a literal, a single variable, B is a literal, D is a literal, C bar is a literal. So individual this variables, they are called as literals. Then next is product term, also called as a mean term. Now any term of the type like A, B, C, or maybe we can have y1 equal to A, B bar, C bar, any term which is a product term. This is a product term, okay, which we get by ANDing A and B and C. Here we have A and B bar and C bar. So this is called as a product term. It is also called as a mean term. Then we have the max term. So max term is also called as the sum of the term. Sum of the term, which is max term. So we have like A or B bar or C. Then we can have A or B or C bar, any such term which is a sum. This is a sum term, ORing, which we get by ORing. It is called as the max term. Next is a standard product term. So suppose if we have a Boolean expression, a function, a logic function, which consists of these four variables. So standard product term will contain all the four variables either in complemented or uncomplemented form. For example, here we can have like a bar, b, c, d bar. All the four are present. So this is a standard product term provided the function depends on a, b, c, d. Then one more, like we have a, b, c, d, any such expression which is either in complemented and uncomplemented. This is a standard product term. In this case, if we write this a, c, d, so here b is missing, so this is not a standard product term, so it is a product. Then standard sum, same thing. If we have a Boolean expression or logic expression depending on these four variables, so this expression or this term is a standard term because it has all the variables a, b, c and d in whether they are complemented or uncomplemented. Here also one example, this one, sorry, this is also an example. So maybe here we can have bar, okay, but this one a or b or d or d bar, so here c is missing, so this is not a standard sum term. Next definition is sum of products, and of course we have product of sum. So why are we running this definition? Because it can be shown that any logic expression can be converted in these two forms. So it would be easier for us to design the circuit, therefore we are using this form. So what is the meaning of sum of product? So any expression of this type, like I am writing this a, b bar, c, this one. So this is a sum of product. So here we have products, these are the products, and we are summing them. This is the summation of the product. So therefore this expression is called as a sum of product. This is not the standard one, we will see standard afterwards. So this is a simple sum of product expression, and it can be implemented by using AND or combination. So first AND gate. So this, to implement this we need AND gate. This every product requires a AND gate, and finally we want to do a summation. For that we require OR. Therefore this is implemented using AND or combination. Then we have product of sum. So any expression of this type, like I am writing this, any complemented uncomplemented form. So this is a product of sum. So here we have a sum, here we have a sum, and we are taking a product of this two sums. So therefore this is product of sum. It can be implemented using OR AND. So first we have to do ORing, and then finally ANDing. Now regarding the standard sum of products and standard product of sum. So in this case, in here, in the first one, sum of product, in this ABC is present, AB is present, and ABC. In this case C is absent, so this is not a standard sum of product. So suppose if we have a function of a Boolean function of or logic function of ABC, it must contain all the terms. If these three terms, any form, any complemented form will do. So this is the standard product, standard sum of product. Then we can also have like this ABC, and so all the terms should be there, all the three variables should be there, whether they are complemented or uncomplemented, they should be there. That is the requirement. Then you can have A or B or C. So this is the standard product of term. So that's all for this lecture. In the coming lectures we will see how to solve the expressions using Boolean algebra and then K-maps. Okay, thanks for watching.